I went to a scientific school, MIT, and in fraternity, when you first join, they try to keep you from being, if you think you're smart, from being feeling that you're too smart, by giving you what look like simple questions to try to figure out what actually happens. And it's like training for imagination, you know. It's kind of fun, and I thought I'd tell you some of them that I remember. I learned them. Of course, once you learn them, the next time somebody comes along with this wonderful puzzle, you look at them kind of quietly, you wait 2 or 3 seconds or 5 seconds to show that you were thinking, and then you come up with this answer to astonish your friends. But the fact was, of course, that you were trained by your fraternity brothers as to how to answer these things early on. One of the questions we got was the problem about the mirror. It's an old problem. You look in a mirror, and let's say you part your hair on the right side. Then you look in the mirror, and the image has got its hair part on the left side. So the image is left to right mixed up. It's not top and bottom mixed up, because the top of the head of the image is up there at the top, and the bottom of the feet is at the bottom. And the question is, how does a mirror know to get the left and right mixed up and not the up and down? You get a better idea of the problem if you think of lying down and looking at the mirror. All right, your hair is still on the left side, and now the left and right was the up and down, whereas the up and down, which look okay, was the right and left before. And the mirror somehow figured out what you're going to do when you're looking at it. So to describe in a sort of symmetrical way what a mirror does, that it doesn't look lopsided, that it takes left and mixes it up with right, and it doesn't do the same with up and down. And after a lot of fiddling, I knew we worked out the answer to that one. You see, if you wave this hand, then the hand in the mirror that waves is right opposite it. The hand on the east is the hand on the east, and the hand on the west is the hand on the west, and the head that's up is up, and the feet that are down are down. Everything's really all right. But what's wrong is if this is north, your nose is to the north of the back of your head, but in the image, the nose is to the south of the back of the head. So what happens really in the image is neither the right nor left mixed up with the top and bottom, but the front and back have been reversed. You see, that which is the nose on the thing is on the wrong side of the head, if you want to. All right? Now, ordinarily, when we think of the image, we think of it as another person. And we think of the normal way that a person would get into that condition over there. It's a psychological thing. We don't think of the idea that the person has been squashed and pushed backwards, forwards with his nose and his head, because that's not what ordinarily happens to people. A person gets to look like he looks in a mirror by walking around and facing you. And because people, when they walk around, don't turn their head for their feet, we leave that part alone. But they get their right and left hands swung about, you see, when they turn around. And so we say that it's left and right interchanged. But really, the symmetrical way, it's along the axis of the mirror that things get interchanged. Well, that's kind of an easy one. A harder one, and very entertaining, was what keeps a train on the track? And, of course, the answer is, as everyone thinks, the flanges on the wheels. You know, the wheels have some kind of flange on them. But that's not the answer. Those flanges are just safety devices. If the flanges rub against the tracks, you hear a terrible squealing. They're just in case the real mechanism doesn't work. There's another problem with trains that's connected to it. People all know this about their automobile, that when you go around a corner, the outside wheels have to go further than the inside wheels. And if the wheels were connected on a solid shaft, you couldn't do that. You can't turn the outside wheels further than the inside wheels. And so the shaft is broken in the middle with a gear system which is called a differential. Did you ever see the differential on a railroad train? No, you look at those wheels under a freight car, and there are the two wheels, and there's a solid steel rod going from one wheel to the other. There's nothing. One turns the same as the other. So now how does it go around a corner, a curve, when the outside wheel has to go further than the inside wheel? And the answer is that the wheels are flanged like this. I mean, not flanged, they're cones. This way. That is, they're a little fatter, closer to the train, and a little thinner further out. If you look closely, you'll see they got this beveled edge. And it's all very simple. When they go around a curve, they slide out on the track a bit so that this wheel travels on a fatter part, a bigger diameter, and this on a smaller diameter. So when they both turn one turn, this swings further than the other. And that's what keeps it on the track also the same way. Suppose a train's running along on this thing, on the track, and the track's here and here, and the two wheels are exactly balanced, and it's nice and even. Suppose accidentally it gets a bump or something and slides out this way. Then this wheel is on a bigger circumference than this one, but they're on a solid shaft. So when it turns once around, it carries this wheel forward relative to the other and steers the train back on the track. Of course, if it gets too far off on the other side, it goes back and forth, and it stays on the track because the wheels are tapered and the flanges are safety. Well, we had a lot of stuff like that we had to learn, to get straightened out before we could become full-fledged members of the fraternity. If I'm sitting next to a swimming pool and somebody dives in, and she's not too pretty, so I can think of something else, I think of the waves and things that have formed in the water. And when there's lots of people have dived in the pool, there's a very great choppiness of all these waves all over the water. And to think that it's possible, maybe, that in those waves is a clue as to what's happening in the pool. That some sort of insect or something with sufficient cleverness could sit in the corner of the pool and just be disturbed by the waves, and by the nature of the irregularities and bumping of the waves, have figured out who jumped in, where and when, and what's happening all over the pool. And that's what we're doing when we're looking at something. The light that comes out is waves, just like in the swimming pool, except in 3 dimensions instead of the 2 dimensions of the pool. They're going in all directions. And we have a 1/8 of an inch black hole into which these things go, which is particularly sensitive to the parts of the waves that are coming in a particular direction. It's not particularly sensitive when they're coming in at the wrong angle, which we say is from the corner of our eye. And if we want to get more information in the corner of our eye, we swivel this ball about so that the hole moves from place to place. Then it's quite wonderful that we can figure out so easy. That's really because the light waves are easier than the waves in the water are a little bit more complicated. It would have been harder for the bug than for us, but it's the same idea, to figure out what the thing is that we're looking at a distance. And it's kind of incredible because when I'm looking at you, someone standing to my left can see somebody who's standing at my right. That is, the light could be going right across this way. The waves are going this way. The waves are going this way. The waves are going this way. It's just a complete network. Now, it's easy to think of them as arrows passing each other, but that's not the way it is, because all it is something shaking. It's called the electric field, but we don't have to bother with what it is. It's just like the water height is going up and down. So there's some quantities shaking about here, and in a combination of motions that's so elaborate and complicated that that result is to produce an influence which makes me see you, at the same time completely undisturbed by the fact that there are influences that represent the other guy seeing him on this side. So that there's this tremendous mess of waves all over in space, which is the light bouncing around the room and going from one thing to the other. Because, of course, most of the room doesn't have 1/8 inch black holes. It's not interested in that light, but the light's there anyway. I mean, it bounces off this and it bounces off that, and all this is going on, and yet we can sort it out with this instrument. But beside all that, you see, those waves that I was talking about in the water, maybe they're so big, some of them, and then you could have slower swashes, which are longer and shorter. And perhaps our animal who's making his study is only using waves between this length and that length. So it turns out that the eye is only using waves between this length and that length, except those 2 lengths are 100 thousandths of an inch. 100 thousandths of an inch, maybe. And what about the slower swashes, the waves that go more slowly, that have a longer distance from crest to trough? Those represent heat. We feel those, but our eye doesn't see them focused very well. We don't, in fact, at all. The shorter waves are blue, the light, and the longer waves are red. But when it gets longer than that, we call it infrared. All this is in there at the same time. That's the heat. Pit vipers that you got down here in the desert, they have a little thing that they can see the longer waves and pick out mice, which are radiating their heat, their longer waves, by their body heat, by looking at them with this eye, which is the pit of the pit viper. But we aren't able to do that. And then these waves get longer and longer, and all through the same space. All these things are going on at the same time. So that in this space, there's not only my vision of you, but information from Moscow radio that's being broadcast at the present moment, and the singing of somebody from Peru. All the radio waves are just the same kind of waves, only longer waves. And there's the radar from the airplane, which is looking at the ground to figure out where it is, which is coming through this room at the same time. Plus the X-rays, cosmic rays, and all these other things, which are the same kind of waves, exactly the same waves, but shorter, faster, or longer, slower. It's exactly the same thing. So this big field, this area of irregular motions of this electric field, this vibration, contains this tremendous information, and it's all really there. That's what gets you. If you don't believe it, then you pick a piece of wire and connect it to a box. And in the wire, the electrons will be pushed back and forth by this electric field, sloshing just at the right speed for a certain kind of long ways. And you turn some knobs on the box to get the sloshing just right, and you hear Radio Moscow. So you know that it was there. How else did it get there? It was there all the time. It's only when you turn on the radio that you notice it. But that all these things are going through the room at the same time, which everybody knows. But you got to stop and think about it to really get the pleasure about the complexity, the inconceivable nature of nature.